today's seminar speaker, Professor Harald Ade. As you might know, Harald is spending some time with us here as a visiting professor. And so today he's going to share some of his work, but I think also I would like to invite you to make contact with him and take advantage of the fact that he's here and have some productive discussions. Let me say a few words about Harald. He was raised and educated in Stuttgart in Germany, but studied in the US, got his PhD at Stony Brook, SUNY, and in 1990 in physics. And then shortly after that, he joined the North Carolina State University in Raleigh in 1992. He has received numerous awards, including the Heinrich Award of the Microbeam Analysis Society in 2000, Young DuPont Faculty Award, an NSF Young Investigator Award, and many others. He's also a fellow of the American Physical Society and AAAS. So Harald, without any further ado, we're really happy that you're here and looking forward to your presentation.
Thank you so much, Bernard. It's a great pleasure for me to be here to give you a bit of an idea of what we're doing, and I indeed look very much forward that this is sort of just the opening of the interaction. I'm sure there are a lot of things that you might not understand the details, and then feel free to come to me, and I would like to at some point set up also follow-up meetings one-on-one with you to learn what you are doing, not just sort of what COPE is doing. So today I'll discuss a little bit what we do with special tools that are based on soft X-rays and how those can be used in order to extract unique information about organic photovoltaic devices. And I'm giving away already a little bit here sort of the punchline that you have asymmetric molecules, semiconducting molecules that have a backbone that is semi-planar, and that backbone can be either face-on or edge-on relative to a bulk heterojunction interface. And that's extremely hard to measure, and yet it might have important implications for the device performance. We also do work sort of using soft X-ray scattering and reflectivity to look at thin film transistors, and that's a whole completely different talk, but if that is something you're interested in, I'm very happy to also discuss that. We can measure in reflectivity interfacial composition fluctuations with a precision of 0.1 nanometer, so at an angstrom level. That's one of the tools, and we can look at correlation length of molecular orientation even if the polymer isn't highly crystalline. So these are some of the unique things. So just in case you, I'm sure here most of you don't need a lot of reminding. What we talk about today is sort of converting sunlight to electricity, and there are a number of technologies. Some of them started way back and they have very high efficiency, and we're concerned here down here with the organic or plastic organic photovoltaics. And while they have lower efficiencies to date, they tend to be very cheap or possibly very cheap and can be put on flexible substrates, etc. And the improvements are also substantial. So this is a fairly large field, as you might know. So we'll look at these and try to find out, what really happens. And so what needs an absorbing layer, at least 120 nanometers thick, in order to absorb a lot of light. You need some organic materials. Here are some of the prototypical fruit fly, I would say, of the field, P3HT and PCBM. They sort of have a different homolumos. I showed that here, and so we'll go into that a little bit later. So what do? You co-dissolve that in maybe chlorobenzene or some other solvent. You cast this in film, and then you get some non-equilibrium morphology, because this is a thin film cast. Then you sort of try to manipulate that morphology in order to get the best performance. And the engineering challenge is that the exciton diffusion length is only on the order of 10 nanometers, and the film thickness is on the order of 100 nanometers, and that means that, you know, I have potentially three-dimensional structures here. And so how do I measure that? And without measuring, how do I know what I get? Am I always stuck in a shake and bake mode where I sort of just heuristically change parameters? So, and the basic principle is, and a lot of this is, the details are actually not really agreed upon yet, except that we absorb a photon, that's clear. And so if we look at this from the donor level, you excite an electron into the LUMO, then that is thought to be a bound exciton that can only diffuse around, so it kind of needs to diffuse to an interface, and there I have an energetic difference here. It can be quenched or split. Potentially I have a charge transfer state. Again, here the details are still under quite a bit of debate, I would say. Then eventually you get charge separation and transport to the electrodes. So that is some of the canonical picture that you often see with just sort of a homolumo of the acceptor, homolumo of the donor, or really charge transfer state, and you see diagrams like this, where they naturally donor acceptor, two phases, two colors. People typically originally have been thinking that these are pure phases. But there's a simple questions. How pure are these phases really? I have a small molecule, a relatively small molecule in a complex polymer. Could it be that the fullerene, for example, is actually fairly miscible? And if indeed I have a mixed phase, you know, then you would think, gee, you know, that leads to a lot of charge recombination, so that would be bad. So it's one of these questions that is indeed interesting to find out. But if you go back to this engineering challenge, if I use a microscopy technique, unless I'm sort of lucky and I have vertical, fully penetrating domains, I usually, if I do this in transmission, I get an average and a projection. So I need a different tool in order to measure this. I need either tomography, which is extremely challenging, or, as we will see, scattering. So maybe just a note here, scattering basically doesn't look at the projection of this, it looks at the correlation in each plane as the X-rays go through. So we can actually get a measure of that, and we average the correlations essentially afterwards with scattering. So how do we measure? Well, unfortunately I don't have a tool in my basement in North Carolina. I have to travel to Berkeley, which is the facility I use, the Advanced Light Source in Berkeley. It's not a bad thing, it's a pretty nice place. My postdocs and students typically don't complain when I send them out there, even though they're on the plane for a while, so far so good. So, and then what do? We have two tools. Special light bulb. The light bulb is $100 million plus. Then there has a couple beam lines, monochromator. We have a zone blade to make a small spot. We can do microscopy. We can change this X-ray energy and therefore can do spectral microscopy. Spatial resolution is on the order of 50 nanometers. And then in order to go to higher spatial resolution, we do small angle scattering, but with soft X-rays. When you do that, you lose the real space picture. You only essentially collect domain statistics information in reciprocal space. So for example, here your eye could easily pick out that I have a certain dominant length scale in this sample, and that would be the radius of this ring. And as the length scale gets smaller, the scattering gets larger, so that's the reciprocal relationship. So just keep that in mind as we go along. And then, of course, if I change the gray levels here and I lose contrast, what would happen? The intensity of my scattering would go down. So using the scattering intensity gives me an idea of what the composition fluctuations are and where I sort of get that size scale here in reciprocal space tells me what the domain size or the domain size distribution is. So that's the one tool. And then What's though unique about soft X-rays relative to hard X-rays? With hard X-rays, I only measure the number density of the electrons, essentially because that is what I scatter from. With soft X-rays, near the carbon atom, I can pick an energy where I basically have a virtual transition to an unoccupied state, and that is why it's called resonant, okay? And this is sort of what you get in the visible light too. So I can get I can either get an absorption or even below the edge I get a resonance, and that makes me sensitive, and I'll show that to you a little bit in detail. I'm getting sensitive to the unoccupied molecular orbitals, and that makes me sensitive to the bonding environment. Okay, so here just some prototypical, these are classic amorphous polymers, not semiconductor polymers, but just to enunciate the principle. So I have polystyrene unsaturation here, I get the sharp resonance that has to do, and this is now in absorption, that has to do with the promotion of an X-ray from a 1s electron into the unoccupied pi star manifold. And with it, there's a dipole transition moment. We have polarized X-rays, and that will later allow us to be sensitive also to orientation of bonds. And then if I go to PMMA, this peak is shifted a lot. The unsaturation is next to an oxygen atom, so there's both initial and final state shifts. Even if I just change one of the carbon atoms in the aromatic ring, I completely change the structure of my pi star. The unoccupied pi levels, and that changes the spectroscopy. So this is a very rich method in many ways. It's not as sensitive as NMR or IR, but it's quite sensitive to the chemical environment that you have an atom in. It's atom specific, element specific, but we can sort of look at what the bonds are. So this is very good. So let's go to that question of how pure the phases are and see whether we can learn something from that. Here I now show absorption spectra of 3 prototypical materials used in organic photovoltaic cells. The blue one is PCBM, the red one is regioregular P3HT, and the green is the MDMO PPB. And you see they're all very different, so we can easily distinguish them. And we have good signal to noise, so we can do quantitative composition maps in the X-ray microscope. Now, I already alluded, though, that in a 3D material where I have a 2D projection, if the domain size is smaller than the film thickness, I'm in trouble. So you have to be a little bit careful how we use the spatial resolution here. So in this particular case, we highly anneal a sample, we create PCBM crystals, and then they deplete the PCBM in their vicinity. So this is a map in the X-ray microscope on a TEM grid where we deplete the PCBM into these crystals. If you map this at the P3HT absorption edge, you see sort of a more uniform matrix background because you're not sensitive to the PCBM, but you can take spectra, line spectra and all that and do this quantitative. So the first indication in the microscope that we've had that indeed, of the first observation that PCBM is miscible in at least the amorphous part of P3HT was in 2009. When we initially were interested in sort of just measuring sort of the diffusion constant, and so we looked at the depletion zone around one of these PCBM domains as a function of time and plotted that and fitted with a Fickian diffusion profile and extracted the diffusion constant. So that was all fine. We also noticed, but at the time didn't fully appreciate what the significance of that was. We also noticed that when we fit this diffusion profiles, it never went to 0 next to the PCBM crystal. It went to a finite value that was on the order of 20% PCBM right next to the PCBM crystal. So that indicated that that is sort of the equilibrium composition of the PCBM in the P3HT, in the presence of a PCBM crystal. And that implies that, if I anneal these devices, I can never get the mixed domains that's more pure than this value. Okay, so this was the first indication that a direct measurement in many ways that is so. We then went further and said, well, gee, now let's actually anneal this and not look at the gradient. So we annealed to very aggressively. We essentially depleted all excess PCBM into these crystals. This is an open area. We can then go with the microscope and measure the composition in these mixed regions. That is the polymer matrix with the residual PCBM in it at that temperature that's in equilibrium at that temperature. Again, two systems here. P3HT of different regioregularity, and then the bottom is PPV with different ratios of the fullerene to polymer. And so as we add more fullerene, of course, we deplete that more into these crystals. So this is a visual representation too, that you deplete all the fullerenes, and we measure the matrix here and essentially get the same value. So that is one way of checking that we measure a thermodynamic quantity here. So when you do that, though, in P3HT, the problem is that the value that we measure, the residual value, isn't directly the value in the amorphous matrix, because the P3HT at that size scale has, and we can't directly see that, has crystals. We know from wide-angle X-ray scattering that there's no intercalation. So basically, one would need to know the degree of crystallinity to convert our measurement into an absolute measurement of what the miscibility is in the actual amorphous region. So besides that, we looked at blend ratio, thickness, etc., and the only thing that we find is that the temperature matters. So therefore, you can sort of look at these miscibility diagrams with the proviso that I just said, that this number needs to be corrected for the degree of crystallinity. And so there seems to be, and that degree of crystallinity has some temperature dependence. So we have to be careful how we interpret this. But you see that these can be fairly large in regio-random. These are sort of up to 15–20%. In the regio-regular, it's more on the order of 5% at typical annealing temperatures. But that still means if I have 50% crystallinity, that I have 20% PCBM in the amorphous phase. And then where's the other PCBM going? It's in an aggregated phase, and so I end up with a three-phase morphology. So this is the implication of these miscibility measurements, is that the morphologies are more complex. You don't have just two pure phases, you have three phases, and if you go through sort of some volume fraction argument, in this case you would find out that the mixed phase in a P3HT cell would be on the order of 40% of the volume. Yes?
I mean, here, these are for amorphous material or crystalline material?
These are crystalline, so these are crystalline. Okay?
So even in the crystalline P3HT
no,
phase,
no, in the crystalline P3HT phase, we know from wax there is no PCBM. But only part of the, it's a semi-crystalline polymer. There is a fraction of no more than 30–50% of the P3HT, even in a homopolymer film, is in a crystalline phase.
So if there is none, why do you have like 2% here? Why?
Sorry?
I thought this represents the concentration of PCBM in the bead.
This represents the concentration of the PCBM when I deplete all excess PCBM. Right. But it's a measurement. This is a phenomenological measurement that averages over the amorphous regions and the crystalline regions of the.
Oh, okay, I see. So it's an average.
Right. It's an average of both, because I don't have the spatial resolution in this measurement to differentiate the two. I could calculate out the crystalline fraction if I do pole figure measurements on the materials with X-rays. But we didn't go through that length in this particular system. So then we sort of went further and did this for a number of other systems, and you see that we basically find that, yes, PCBM is, these are again just the I should always put the miscibility here in quotes, because that's the phenomenological measured quantities, but they on the order of 10, 20, 30%, so they can be quite high. And what we find is if it's extremely high in one case, then the performance, of course, suffers. But all of these devices work to some degree. And so what's the role of this? And is that good? Is it bad? Do I want high? Do I want low miscibility? When I now do a chemical synthesis, I don't only have to worry about the HOMO-LUMO engineering, etc., solubility in a solvent. I also have to worry about the interaction with the PCBM in terms of miscibility or whatever interaction, chi, if you want to think of it in those terms, because that influences the phase morphology that you get in a device. And now later get to another material, the AFTAS, and there we did some solvent annealing at room temperature, and we measure very, very low miscibility. This happens to be a very good device performance and very interesting material, and that's why, we raised the question, is low actually very good? Is indeed this original idea of having two pure phases not so wrong after all, but how do we get there in terms of the design of the chemistry and the molecules so we can achieve that? All right, so that's the story on the miscibility with an impact on the morphology. Rather than just having two phases, we sort of have three phases, and people have sort of tried to draw all kinds of diagrams, and I just want to put that out there, essentially saying that, even after all this work, we still don't know what the real morphologies are. And I will later conclude that we still actually don't understand what the actual morphology is. So let's look at this a little bit, what the ideal morphology is. So now if I have three phases, okay, I have an acceptor aggregate and a donor aggregate. And it's not just something that happens in space, because these materials interact, the electronic structure changes. Okay, if I have an isolated PCBM, it has a different electronic structure than if I have an aggregated PCBM. And that's what you get in the UV-Vis spectra of aggregation of polymers. That immediately tells you that. So if I now have an amorphous region, and we know the regiorandom P3HT has a very different UV-Vis spectrum than the more crystalline regioregular one. So what I'm getting is I'm also changing the electronic landscape. Okay? Oops, I want to go back. So that means that essentially the band gap is different. We're not quite sure how these things align, but basically I sort of have the aggregate has a smaller gap. And so if I now excite sort of in this mixed phase, that's not a problem, because my electron still likes to go to the aggregate, and my hole still likes go to the polymer. And that may actually be good. I might actually want to optimize the volume of that region, because this is one mechanism to drive the charges possibly out, okay? If I have enough connectivity of the aggregate phase to the electrodes. Now if I absorb though in the polymer or in the aggregate phase, okay, it certainly wouldn't want to go as a whole through the polymer. It would have to go as a whole, as an electron through the polymer. It would have to split at this interface and go as an electron through the mixed phase, and the same is true for the hole. So that has implications that essentially the effective charge transport is via these energy levels, and that means in the mixed phase I must have enough charge transport, efficient charge transport, and minimize the recombination losses. So that's the challenge. So I think there are implications in terms of electronic structure, and I'm sorry I haven't yet sort of tried to really make representations of what that means. But basically there's sort of implications here that if I were to, let's say, just have a mixed phase in between the red and the blue here, make that purple, okay? That would work very well for absorption in the mixed phase, And, but it wouldn't work very well unless I had good charge transport in the mixed phase for absorption in the red phase. So I have to engineer sort of that transport, and we have this a couple studies now that show, and I will allude to that later, that if, for example, the fullerene concentration in the mixed phase is too low, then you lose the charge transport in that domain and the device suffers. So besides just compositional variations in 3D, we have asymmetric molecules, at least let's say at least one of the components in a fullerene device. So I need to also consider ordering in terms of orientation. And there's quite a bit of support for that from bilayer small molecule studies. So if you look at phthalocyanine fullerene heterojunction and you control that orientation, you see that by controlling that by growth on a different substrate, you see that there's a difference in performance quite a bit. And then this is actually worked in here, theoretical studies in the Preda group that show that indeed there's a difference between phase and edge-on in terms of the charge separation efficiency at this versus this interface. And so now, you know, what does that mean for a bulk heterojunction solar cell where I have a complicated 3D interface? What does an interface even really mean when I have three-phase morphologies? So there are a lot of complicated questions. Some other work calculations also showed, you know, that you have sort of, even in these materials, you would expect to have a dipole at the interface, and that gives you band bending, and it changes the electron affinity and all those things, again, as a function of orientation of material. I think this was pentacene C60. So depending on how the pentacene is organized, you change the electron affinity and ionization potential of these things, and that changes how the essentially the electronic structure at the interface. So this is all sort of relevant, and now, but how do we measure that? How do we control that in a bulk heterojunction interface? Are these things important and relevant? So these are some of the things we try to get at in a bulk heterojunction interface. So I just want to remind you how we measure. We do the microscopy, we do the resonance scattering, and that is sort of the biggest tool that I will use for the rest of the talk. And it will give me chemical sensitivity. And because I have a dipole selection rule, when I excite into a pi star orbital, I am sensitive to orientation. And then as a complement, we also do grazing incident, wide-angle X-ray scattering, and I just want to give a quick tutorial how that works so you can see how all these pieces hang together. So basically in grazing incidence, you come in at grazing incidence to your sample, you have a 2D detector, that is what you see, so I'm scatter off the sample, and then you can see sort of a bunch of peaks here, and they're not circles, okay? You look at that, so this would be P3HT, 100, 200, 300 reflection of the lamellar spacing, okay? So this would be this here. So if I have, phase on edge on right, this is actually the lamellars would be, this is in the direction this way, so this is out of plane. So if the substrate is here, indeed, this would be lamella this way, okay? So it's edge-on relative to the backbone. So the backbone would be edge-on, the lamella are out of plane, therefore I can see the diffraction peaks of the lamella. There's a PCBM, diffuse halo, that I can also evaluate that to see how much aggregation I have. If the PCBM is completely dissolved, I wouldn't see that as well. And then here's 101 peak, that corresponds now, this is at larger Q, so it corresponds to a smaller spacing. So that is the pi-pi stacking direction, okay? So here I would see a component of it in the out-of-plane pi-pi stacking direction that corresponds to this amount of signal in the in-plane direction of the 100. So this is the highly ordered fraction of the polymer. Then I can see in the wax how well it is ordered. I can measure from the width of this what the coherence length or size scale of this ordering is, and I can see the orientation. And then with the scattering, we look at the amorphous parts, we look at all of it, and we look at other length scales. So let's go through an example here and use PDB7, which is one of the high efficiency materials. Co-dissolved in chlorobenzene with and without DIO. We want to know what happens to the morphology. So without DIO, you get a typical JV curve like this. And just as a refresher, sort of the fill factor is sort of how square this graph is. The VOC is the open circuit voltage and the short circuit current. So these are the three phenomenological parameters that sort of describe the overall performance of the device. So you see with the DIO, I essentially gain a lot in short circuit current. We can also measure the external quantum efficiency. You see that goes up, and there's a little bit more improvement in the region of the PCBM near 450. Down here, that's the polymer absorption. So the morphology, something changes. What is it? Those are the questions that you would like to understand. You can use TM. This is with and without. With and without. PM gives you sort of domains. It's sort of hard to make out what you have here with the DIO. And besides that, this is bright field TM, so I don't really have a quantitative measure for the purity, so I don't know how pure these domains are. And so those are the things one would like to know, and we will use sort of X-ray microscopy and scattering. Here are the differences in the spectra. They're very large, so I can use that to give me quantitative compositional analysis. All right, so if I do this now with X-rays and the size scale has a little changed, I get very nice images for the domains that are large. I can do a quantitative composition map. I struggle in real space. I'm reaching the size limit that I can look at, and maybe I have a 2D projection of a 3D structure. So with DIO, the real space X-ray microscope also struggles. If you look at the line scans here, you see that the PCBM droplets are nearly 100% PCBM. These are quantitative measures. By the time you deconvolve sort of the response function of the microscope, and we know there's a wetting layer on those domains, we conclude that essentially the PCBM are pure domains, more or less. You see that in the matrix out here, we have something like 30% PCBM. All right. And the blue one is sort of that sample. We just don't have the spatial resolution to look at that. So we wondered, this in the matrix, how does that relate to the fundamental miscibility limit? And so if we actually aggressively anneal these devices for 5 days, so this is now at the temperature where you didn't create sort of the device, but it's nonetheless interesting that in PDB7, the miscibility residual fullerene measurement that we have next to this PCBM crystal is 30% PCBM, and that is essentially what we have in the matrix here. So, and I think it would be hard to imagine that I can have a non-equilibrium process like spin casting that would actually give me purer domains than what this miscibility limit is. And so in this situation, you actually reach these thermodynamic limits. I think we're close to that. All right. So we're still having problems, though, to understand what happens with the DIO. So now we do scattering. And there we can sort of, and I didn't allude to that completely, I have a real part, but also an imaginary part. And the scattering contrast is equals to the delta real part squared plus delta imaginary part squared. It's a delta n squared. It's the same than what you would have in the optical. So we can fully understand sort of this materials contrast, and so we can use that to look at things. So we get sort of this 2D scattering in transmission. So this represents the in-plane structure. We get a distribution of the scattering. This is Lorentz corrected for some of the audience here, if you understand. So we just integrate, but historically I of Q was a one-dimensional quantity, so the proper total scattering intensity is this historical quantity Q squared. So this is my total scattering intensity as a function of Q. So you see there's a distribution. There's sort of a characteristic length scale also referred to if I translate that back into real space of the long period. So that's fine. So we can do that. We can integrate this, and that goes back to what I said earlier. You know, if I have just light gray and dark gray, I get less scattering than when I have black and white. So I can look at that total scattering intensity, and I can do that as a function of photon energy. And I can look at whether that follows the materials contrast or vacuum contrast or something else. So in this case, we have excellent correspondence to the materials contrast, and that means I know that whatever scattering distribution I get here is actually from the compositional fluctuations in the sample. So this is a nice thing that you don't have with hard X-rays, and it's hard to do with neutrons as well. And it's particularly important later on when you have additional scattering from orientational correlations. So now we do scattering from these samples as well. And so here are the scattering distributions. It turns out it's a beautiful log normal distribution for the DIO. And without DIO, there are two log normal distributions. I'm not quite sure what causes that in terms of the phase separation mechanisms. But nice log normal. The spacing is rather different. We integrate the scattering intensity, and that is sort of different by 10%, but the composition fluctuation is the square root of that. So within 5%, essentially, the composition fluctuations, and therefore the relative domain purities are the same in these materials. And that is something that you can pull out from the scattering that you wouldn't know otherwise. So really, in this particular situation, the only difference that gives me here sort of this increase is the domain size is smaller. We've measured it. We measure the purity. So just a note here. I think when you transfer back this log normal distributions in real space, we might not have gotten that quite right in this publication. All right. So we now use this in a number of systems where we can look at the relative domain purities through the total scattering intensity. One of the systems was from WAU, where we have sort of a particular material and DTBT, and we can do fluorine substitution, either 1, 2, or 2. And you see that the more fluorine substitution, this is now a scaling exponent that measures how much bimolecular recombination I have in a device. Okay, and so you see that the blue one here is the closest to 1, and that tells you that you have the least amount of bimolecular recombination. You see there's a systematic evolution with the fluorine content. We measure the purity from the scattering, and what we that the putting fluorine on there decreases the miscibility and improves the purity of the domains. So more pure domains, less bimolecular recombination, which is sort of what you would expect. And then we use the wax to look at side chains, and this is just the reminder that we can do sort of this, and we look at crystallization. And for a long time, people thought, yes, crystallization and phase-on orientation relative to the substrate is important, and it may be important, but it isn't always the only driver. In this particular case, while the side chains modifications increased the crystallinity, it didn't lead to higher performance. So it's in other parameters of the device. And then there's sort of a special material, FTAS, and I'll come to that later. Again, fluorinated from the use group, where we find sort of an insensitivity to domain size and purity. Now you go like, what? Right, you know, that's sort of is against the sort of all the paradigms that you have. You would expect bimolecular recombination and exciton splitting to both depend on size, scale, and purities. In this system, over a range of parameters, it's rather insensitive. So why does that still work so well? And you can only ask that question that once you know that indeed this is insensitive. So I'll go into this in a detail if I have time. I want to now come back to this orientation with respect to this complicated, possibly 3D interface in a donor acceptor system. So in this particular material, PNDT, DDTBT, again, with or without fluorination, depending on the processing, we get very different scattering. You see some of this asymmetry. You've seen that earlier, but I haven't explained it yet. And this asymmetry in the scattering has to do with the local orientation relative to a reference. And I try to explain that to some degree, but just as a highlight up front, this asymmetry we interpret as a phase-on orientation relative to the PCBM domain. We're not totally sure it extends all the way to the interface, but you have sort of arguments why that would be. If over here we have mostly isotropic orientations or slightly edge-on if you analyze this scattering asymmetry. So asymmetry, reverse asymmetry, but not as big a signal. So how do we, how do we analyze that and relate that to device performance? So what we do is we just look at sector averages. So here, this is the full sector, and then this is sort of a vertical and horizontal sector. We integrate the sector average total intensities, and we look at the difference over the sum. So that's a phenomenological parameter that's easy to calculate from the data. So we look at this anisotropy ratio, essentially, of the scattering pattern and analyze that. You can do that as a function of photon energy, and you see that there's a rich difference. I can flip sort of the contrast. Okay, this anisotropy changes as a function of energy. This is the same sample. We use this in order to understand where that comes from and how to interpret it. So I'll again go a little bit into that, but yeah, I think I'll be fine. So if you look at sample for pentacene, right, it's sort of my prototypical here asymmetric molecule. And you know from UV-Vis that, of course, if I have polarized light, the absorption with the polarization in and out of plane would be very different. Okay, in the visible, the dipole transition moment is in plane. In the X-rays, because I start from a spherical orbital at the 1s level, it's the dipole transition moment is perpendicular to the plane of the molecule. Now, when I look then at the absorption, of course, that changes, and visit the real part of the index of refraction as well through a chromoscronic relationship. So I'm very sensitive to this orientation as a function of photon energy, both at absorption edges, but also below the absorption edge through the difference in the real part. And so that's where the anisotropy below the absorption edge comes from. And so let's just think a bit what that could be. If I make a grading of pentacene molecules with nothing, okay, white is, let's say, white would be vacuum, and I line this up so that my transition dipole moment is parallel to my electric field, and therefore I get high absorption. If I had an energy where I get high absorption, I would get high absorption, nothing, high absorption, nothing. I rotate that pattern. Now my transition dipole moment would be perpendicular, so I get lower absorption, nothing, lower absorption. So obviously I get more scattering in the vertical direction than in the horizontal direction. And that would be even if I sort of had sort of now these domains be squares as sort of the simplest situation that I can imagine right now in order to just understand the principle. So I would get more scattering in the vertical, less scattering in the horizontal. If I have sort of, now I can imagine that I have sort of I have a specific PCB pentacene orientation within this bar that would essentially rotate around. So that's, and we can look at this a little bit more complicated. So if I had a round PCBM domain in with the polymer on the outside and the polymer would be face on all the time, then my transition dipole moment would rotate. It would modify my optical constants. I would get high absorption here, which changes, low absorption here because the dipole moment is perpendicular, which gives me a high delta. Here I have more absorption, which gives me a lower delta, and the PCBM is fixed, and we can go through this and sort of look at this more coarse-grained and make it rather square, make it round with 6 sectors. No matter how I simplify it, what you'll always find, or how I arrange this hexagonal grid or square grid, you'll always get a situation where you end up with more scattering in the vertical than the horizontal because I have face-on orientation as expressed through these optical constants. So this is a little tedious, and I'm not going to drag you further through this, but I just want to show you that we've done the work. We go through these optical constants, so we do the transition dipole moment perpendicular and parallel, the contrast flips here, and we can model this, and more or less we get the shape right, except for this spike, we get this right, and below the edge we can therefore sort of see what's going on. In real space, and this is from a different material just to visualize this a little bit. So I have dispersion domains in a polymer matrix. These are 2 polymers. N2200 is sort of the more circular domains. Now if I flip the electric field, my polarization, the matrix sort of gives me more pattern that is vertical here and more horizontal here. If I look at the Fourier transform, which is what I would expect to get in scattering, I get lobes that are horizontal here, and I get the lobes that are vertical here. So I think we are on a way to create a coherent picture of how to interpret that. The first time we've observed this scattering anisotropy was maybe a year and a half ago. So that hasn't really been seen, but I think it will be a great tool to look at devices. So now let's compare this. We observed this anisotropy. We figured out where it comes from. We understand the energy dependence. And so now let's go back to the device performance. So I have the material with and without fluorine, and I can cast from chlorobenzene or dichlorobenzene. I get 4 devices. And I get sort of, the worst device has the slightly edge on. This device has the face on. We quantify this and we get very good correlation, both for, we quantify this degree of molecular orientation. That's essentially the anisotropy parameter normalized through a model for the JSC and the fill factor. Okay, but how about the rest of sort of things? Crystallinity, domain size, domain purity, you know, fine, you got a correlation, but you know, are there other things that correlate? So I look at the domain spacing. This is my essentially the mode in reciprocal space transferred back into real space, and you see there's not a good correlation to the JSC. It's particular this device here, which is the dichlorobenzene hydrogen. It doesn't matter where I have that domain size, it just doesn't give me good correlation. Okay. Then I can look at sort of the relative domain purity. That's when I integrate the total scattering intensity. And again, you know, it doesn't work out. So these composition fluctuations don't seem to matter in this device. I can look at the wax and analyze now the intensities in these diffraction peaks. This is the 100. So you can see here, if I cast from the dichlorobenzene, okay, then I get much better crystallinity, but at the same time I get the best and worst performance. So again, crystallinity doesn't matter. If I look at the pi-pi correlation, I get maybe a little bit a better relationship, but no matter what we analyze, there's no good correlation to the crystallization. So it looks as if in this particular material system, what really matters is this molecular orientation correlation relative to an internal three-dimensional interface, and that's the bulk heterojunction interface. And so just going back to that, there's indeed support that this is important from model bilayer systems. And I would love, of course, to calculate for this particular material what the edge versus face-on situation is. So now we look at other systems, and we now have a tool to measure this edge versus face-on relative to the donor acceptor interface. And what we find is that essentially in almost all systems that we look at, this is the TAS system with hydrogen. I get worse performance than with fluorine. Here too, as I fluorinate, I again change the performance, and every time I get more face-on orientation. This is another system where the backbone changed and drastic difference. The high performance is again face-on relative to the interface. In this case though, the domain size and purity also changed a lot, so one couldn't really draw conclusions. So let's go to the mystery system that has some face-on ordering. That's this FTAS fluorinated. And what's so great about this material is you can go to a micron and still get very good fill factor. Okay, so there's something intrinsically working very well in this material. And you want to be at least here in terms of efficiency, in terms of thickness, but also just from a processing latitude. You know, you wouldn't necessarily want to have to control your thickness within a 10 nanometer. You want to be out here and still get good performance, or some screen printing techniques might make it difficult to go to controlled small thickness anyway. So this is an interesting material. We look at the thickness dependence. What you see here is the resonance scattering that basically says the domain size distribution doesn't matter. It's the same, I should say. It's the same as a function of thickness. So very often that's not the case. The thicker films dry slower, they solidify differently, and the domain size changes. Here it doesn't. When we then look at the relative composition fluctuations, you see that it plateaus immediately after a certain value. It's actually the thinnest films that most likely tries the fastest, where you freeze in sort of the largest composition fluctuations. So you reach high purity relatively quickly, and the degree of molecular orientation is only not a strong function of thickness. Okay, so it falls off a little bit as the film gets thicker. So this seems to indicate that this is a nice system to study sort of intrinsic bimolecular recombination rate. This is again the scaling exponent that tells you what the bimolecular recombination is as a function of thickness. Here's the light intensity fill factor measurements. So we now have a tool to sort of look at this, and maybe this allows sort of some real careful modeling as to what is happening in the system. So, but it's strange. If I now change the solvent, okay, in the film thickness mesh study, we use the same solvent all the time. We always get the same domain size distribution. If you use different solvents, the situation is rather different. So here we have 3 different solvents, and frozen short and long annealed for the trichlorobenzene means frozenness. They immediately take it and put it in a vacuum. And short is sort of they put a Petri dish on top of it, and the residual solvent gives you a bit of solvent annealing. And so we get these resonance scattering curves that give me different domain size distribution. I can integrate that. That gives me the composition fluctuations, so I can again look at that. And you find that, you know, the relative composition fluctuations sort of over a 20% range have almost no impact on the performance. It's only when the composition fluctuations are very small, and that means the domains are very impure. That's when I take a hit. Strangely, the very impure domains correspond to small domains. It evaporates the fastest, so that's also clear why that happens. But then again, the fill factor. Sorry, this is still the fill factor discussion. So both JSC and fill factor within a certain range, not strongly affected. Now we look at the domain spacing. That is changing. And again, what you find is, the fill factor or the JSC is not that strongly dependent. This green one, the dichlorobenzene, is really not because of the size, it's because of the purity. So we're just dumbstruck to some extent, because there got to be something intrinsic in the material that makes this a good material, and we're very curious to find out what that is. And again, maybe some theory may be very useful to elucidate that. All right, so now back to the wax. So the P3HT was semi-crystalline, and we look at that in terms of the AFTAS, okay? And you see there are too many peaks in here. So even as a function of solvent, it's not a highly crystalline material. It's relatively amorphous. The size scale doesn't seem to matter. So the composition fluctuations don't seem to matter. So this is really flies in the face of a lot of the assumptions that the field has, that high crystallinity is good, et cetera, et cetera. So what's so intrinsically good about this material? All right. So, and here's just a summary that, the P3HT is rather unusual. From the wax, I get relatively high crystallinity, and resonance scattering, I get a Gaussian distribution. Most other materials, I get log-normal distributions because the phase separation process is different. P3HT, the crystallization drives the morphology, and the other materials, it's something else. And so for most of these materials, we get this log-normal distribution and relatively low crystallization. And coming back to this measurement of the AFTAS thermodynamic interaction, solvent in yield, the PCBM miscibility that we measure is very low, so they're intrinsically relatively highly incompatible, and that may be part of why things work so well. So that's an angle to look at. So let me summarize the methods here in a way. That's what I wanted to convey in the context of the devices, that we have soft X-rays that can look at domain size distribution, interfaces, purities, and now also molecular orientation, relative, and possibly add the donor acceptor interface. If I have another 5 minutes, I have another story, but I can skip that. What are you? Okay, I just want to do you one thing, okay? And I'm just extremely proud of the quality of data that we have now. So this is a material cast from different solvents. We get extremely good fits with 3 log normals. We can understand them from the energy dependence, that the lowest Q peak is the thickness or roughness fluctuations. The other ones are composition fluctuations. So this is clearly a hierarchical system. We get a correlation of one of the length scales from the soft X-rays with the coherence length from the hard X-rays. Very nice correlation there. There's a correlation between the 2 length scales, the high and low Q peak. So there's sort of a almost scaled relationship where you end up with almost precisely 4 of the small domains give you the large domains. And the small and large domains have an anti-correlated composition fluctuation. And that's also interesting. It makes sense as I draw sort of material out of a nanophase into the macrophase. I'm changing the relative composition fluctuations that I'm measuring. So that's the first time that these details of a 3-phase system, which is implied by these measurements, could be measured. And this is work in progress. You can correlate this now to the structures. And I just want to point out, this might explain why this material isn't working so well. Particularly the polymer component of the material has a low IQE. And so this length scales of this nanophase separation is too large, And in this particular case, the polymer aggregates too strongly. So now you might want to use the side chains to disrupt that or process it differently from a hot solvent. But we use that in order to learn a lot of things about the morphology. Coming back to the ideal morphology, I'm not sure we've figured that out yet. Okay, we've learned a lot, but a lot still remains unknown, both in terms of the mechanisms, how the morphologies get created, how we control it, how it relates to the chemical structure. So the field is sort of, from the morphology perspective, is wide open. Even from the photophysics is wide open. So I think, you know, this is still a good time to get involved. And so if some of you students are still thinking about it, here we go. And again, you know, what's this ideal morphology? We don't know. So let me thank you for listening. This is my group, relatively small. Brian Collins, John Templeton were two of the postdocs that have done the majority of the work, and I get a fair bit of help out at the Advanced Light Source, and my main funding is from the Department of Energy. With that, thanks again.
Thank you very much. Fascinating talk. Do we have time for some questions?
If you go back to slide 51.
51. Yeah. Oh, I actually didn't have it on all. Right.
So, like trying to connect the dots. So this is to me some sort of summary.
Right.
So in an ideal case, so top there in that circle. So that domain size shouldn't matter.
Well, no, I think it does. I think the domain size and purity matters, okay? But I think it might depend on the material, okay? I mean, clearly we know that if the domains get too large, we get bad performance. If the domains are too large and too pure, you go back to the DIO, to the PDB7 example, the device performance isn't very good. I need to use the DIO in order to control the size.
So it's not about the fact that we have two separate faces. We have these aggregations, but what matters is just the boundaries. The first part of your talk is
right. So I have a photon absorption. I need to sort of create charges, and I need to transport charges. And in these three things, I think it tells you already that almost everything matters. Okay, there's sort of one component that I haven't really, and where this schematic may be misleading, is I need enough percolation between these domains. Otherwise, I can split the exciton and all that, and I get free charges, but I can't get them to the electrodes. So, and that's, so the connectivity and the percolation of the charge transport network is also important.
I hate to interrupt the discussion because really that needs to be followed, but unfortunately we have a little bit of a logistic problem because there's a class that's about to start in 1 minute, so we have to leave it here.